In July 2012, physicists at CERN announced the discovery of the Higgs boson. The announcement was made at a seminar in Geneva, broadcast live around the world, attended by Peter Higgs himself, who was 83 years old and wept when the result was confirmed. The discovery completed the standard model of particle physics, the theoretical framework describing all known particles and forces. It was the last missing piece of a puzzle that had taken 50 years to assemble. It was one of the greatest moments in the history of science. In July 2012, physicists at CERN announced the discovery of the Higgs boson. The announcement was made at a seminar in Geneva, broadcast live around the world, attended by Peter Higgs himself, who was 83 years old and wept when the result was confirmed. The discovery completed the standard model of particle physics, the theoretical framework describing all known particles and forces. It was the last missing piece of a puzzle that had taken 50 years to assemble. It was one of the greatest moments in the history of science. Let me give you the full context of what the Higgs discovery meant, because the emotional weight of that moment in Geneva reflects something specific about the history of physics that is worth understanding. The Higgs mechanism was proposed independently by Peter Higgs, Francois Englert, and Robert Brout in 1964. The mechanism explains how the W and Z bosons of the weak force acquire mass while the photon remains massless. Without the Higgs mechanism, the electroweak theory would predict massless W and Z bosons, which is inconsistent with observation. The W boson is approximately 80 times heavier than the proton. The Higgs mechanism breaks the symmetry of the electroweak theory in a specific way that gives the W and Z mass while preserving the photon's masslessness. The mechanism requires the existence of a scalar field, the Higgs field, that permeates all of space and has a non-zero value in the vacuum. The Higgs field is different from every other field in the standard model. It is a scalar, meaning it has no preferred direction in space-time, and it interacts with other particles in a way that gives them mass proportional to the strength of the coupling. The Higgs boson is the quantum of this field, the particle you produce when you excite the Higgs field. Predicting that it existed was easy, finding it was extraordinarily hard. The Higgs boson is unstable, decaying in approximately 10 to the minus 22 seconds after production. It is produced rarely in proton collisions because it has no color or electric charge, meaning it cannot be produced by the strong or electromagnetic force directly, but only through quantum loops. It must be identified in the rare cases when the products of its decay can be distinguished from the enormous backgrounds of ordinary strong force processes. The Large Hadron Collider was built to find the Higgs boson and to search for new physics beyond the standard model. The LHC is a circular accelerator 27 kilometers in circumference, buried under the French-Swiss border near Geneva. It accelerates protons to 6.5 TeV per beam, colliding them at a center of mass energy of 13 TeV in run 2 and 13.6 TeV in run 3. Each proton-proton collision produces a spray of particles that the ATLAS and CMS detectors, each weighing approximately 7,000 and 14,000 tons respectively, record and analyze. The LHC turned on in September 2008 and immediately suffered a catastrophic electrical failure that required more than a year of repair. First collisions at significant energy occurred in late 2009. The data that led to the Higgs discovery was collected in 2011 and 2012 at 7 and 8 TeV. On the 4th of July 2012, both ATLAS and CMS announced 5 sigma observations of a new particle with properties consistent with the Higgs boson. Peter Higgs and Francois Englert received the Nobel Prize in Physics in 2013. Robert Brout had died in 2011 and was not eligible for the prize. The teams of thousands of physicists and engineers who built and operated the LHC and the detectors were cited in the Nobel announcement but cannot receive the prize individually because of the Nobel's limitation to a maximum of 3 laureates per year. And it raised a question that nobody in the auditorium said out loud, but that every physicist in the room understood immediately. Now what? The Higgs boson was expected. It was predicted by the theory. Its discovery was a triumph of the Standard Model, not a challenge to it. What the Large Hadron Collider was also supposed to find: the particles predicted by the extensions of the Standard Model, the supersymmetric partners, the dark matter candidates, the signatures of extra dimensions had not appeared. The LHC had found the Higgs and nothing else. In the years since, the LHC has continued running at higher energies and higher luminosities. It has accumulated unprecedented data sets, and it has continued to find nothing beyond the Standard Model in direct searches, while accumulating a set of precision anomalies, deviations from the Standard Model in precise measurements that are individually uncertain but collectively suggestive. I described several of these anomalies in the W boson mass video: the CDF result of 7 sigma, the muon anomalous magnetic moment at 4 sigma, the B meson anomalies at LHCb. But I want to come back to the broader question that these anomalies raise, because I think the full picture of what CERN has found and what it might be pointing to is more interesting and more significant than any individual anomaly. The question is this: is the Standard Model complete? Not just approximately complete, not just missing gravity and dark matter and a few unexplained parameters, but complete in the sense that no new particles or forces exist at energy scales accessible to current or near-future experiments? The LHC has run at 13.6 TeV center of mass energy in run 3. It has found no new particles. The high luminosity LHC, scheduled to begin operations in the late 2020s, will run at the same energy but with 10 times the luminosity. Future colliders, currently in the proposal stage, would operate at 100 TeV. If those find nothing either, we will be in a situation unprecedented in the history of physics, a theory with no known errors and no known successor. I want to take you through the specific result that is most significant for the question of whether CERN has opened a door to new physics, which is not a single dramatic measurement, but a pattern of evidence that has been building over several years. And then I want to explain what lies on the other side of that door, if it is real, and why it would change physics more fundamentally than any discovery since quantum mechanics. Let me start with the specific result that generated the most discussion among particle physicists in 2022 and 2023. The combination of anomalies that some researchers describe as hints of a violation of the Standard Model's prediction for the properties of the Higgs boson. The Higgs boson was discovered at a mass of approximately 125.09 GeV. Its properties have been measured in detail by both ATLAS and CMS, the two general-purpose detectors at the LHC. The Standard Model makes specific predictions for how the Higgs boson decays, how often it is produced in different processes, and how it couples to other particles. These predictions are among the most precisely calculated in the entire Standard Model, because the Higgs couplings to other particles are directly proportional to those particles' masses. The current measurements of Higgs couplings are consistent with the Standard Model predictions within the current experimental uncertainties, which are typically at the 10 to 20% level for most decay channels. But several hints of deviations have appeared. The rate of Higgs boson decay to 2 photons, one of the discovery channels in 2012, has been measured at a rate approximately 10 to 15% higher than the Standard Model prediction in some analysis channels. This deviation is not statistically significant by itself at roughly 1 to 2 sigma, but it has been persistent across multiple analyses and multiple run periods. The Higgs coupling to charm quarks, one of the lighter quarks, is predicted to be very small and has been searched for but not yet definitively measured. Constraints have been set that are consistent with the Standard Model, but also consistent with a charm coupling that is several times the Standard Model value. New physics models including Higgs compositeness models and certain 2 Higgs doublet models, predict enhanced charm couplings that would be within the reach of LHC run. 3 measurements: the search for the Higgs boson decaying to a Z boson and a photon, a rare decay with a branching fraction of approximately 0.15% in the standard model, produced an interesting result in 2023. Atlas and CMS combined their data sets and reported a first evidence-level observation of this decay, with a measured rate approximately 1.9 times the standard model prediction. The significance was 3.4 sigma, which is evidence rather than discovery in the particle physics convention, and the central value of 1.9 times is substantially higher than the prediction of 1. This result attracted considerable attention. I want to be precise about what a 3.4 sigma result at 1.9 times the standard model prediction means, because both the statistical significance and the central value matter. 3 sigma results in particle physics have historically had a mixed track record. Some have turned out to be genuine discoveries, such as the early observations of the W and Z bosons. Others have dissolved when more data were collected or when systematic errors were better understood. The 3.4 sigma result for Higgs to Z gamma is intriguing but not conclusive. If the rate of Higgs to Z gamma is genuinely 1.9 times the standard model value, it would require new particles running in the loop diagrams that mediate this decay. The Higgs does not decay to Z gamma at tree level. It requires a quantum loop involving virtual particles. The particles in the standard model that contribute most are the W boson and the top quark. New charged particles at the TeV scale could modify the rate, either increasing or decreasing it depending on their quantum numbers. This is the pattern of modern collider physics, not the clean discovery of a new particle at a specific mass, but the accumulation of small deviations in precise measurements of known particles. The deviations are in the few sigma range, individually explainable as statistical fluctuations, but pointing collectively towards something that the standard model does not contain. Now let me take you to the broader theoretical landscape that these results are illuminating, because the question of what is beyond the standard model is not just a matter of waiting for the next measurement. It connects to the deepest unresolved questions in fundamental physics. The standard model is a quantum field theory based on 3 gauge symmetry groups and the Higgs mechanism for symmetry breaking. It describes matter particles, the quarks and leptons, and force particles, the gauge bosons. It is extraordinarily successful. Its predictions have been confirmed at the level of 1 part in a billion for the electron magnetic moment, and with high precision for hundreds of other quantities. But the standard model has several features that suggest it is not the final theory. Let me describe each of them in enough detail to understand why they are genuinely concerning rather than merely philosophical. The hierarchy problem is perhaps the most theoretically compelling sign of incompleteness. In quantum field theory, the mass of any scalar particle receives quantum corrections from virtual particles running in loops. The Higgs boson is the only fundamental scalar in the standard model. Its mass receives corrections proportional to the masses of the particles in the loops. The most significant corrections come from the top quark, the W and Z bosons, and the Higgs boson itself. If the standard model is valid up to the Planck scale at approximately 10 to the 19 GeV, the quantum corrections to the Higgs mass squared are of order the Planck mass squared times a dimensionless coupling. The Planck mass is approximately 10 to the 19 GeV. The Higgs mass is 125 GeV. To get from the Planck scale corrections to the observed Higgs mass requires a cancellation between the bare Higgs mass and the quantum corrections to a relative precision of approximately 1 part in 10 to the 34. This extraordinary fine-tuning is the hierarchy problem. The fine-tuning is not forbidden. The standard model is mathematically consistent with any value of the Higgs mass. The bare mass is just a parameter that must be adjusted to match observation. But the fine-tuning is deeply unnatural in the sense that a tiny change in the fundamental parameters would produce a Higgs mass completely different from what we observe. The universe appears to have chosen, from among many possible values of the Higgs mass, the one that requires cancellations to 34 decimal places. This is either an extraordinary coincidence or a sign that there is physics at the TeV scale that naturally produces the observed Higgs mass without fine-tuning. Supersymmetry was, for decades, the favored solution to the hierarchy problem. In supersymmetric theories, each standard model particle has a superpartner with opposite statistics. Bosons get fermionic partners, and fermions get bosonic partners. The quantum corrections to the Higgs mass from standard model particles are exactly canceled by the corrections from their superpartners if the superpartner masses are not too different from the standard model partner masses. The cancellation is not a coincidence or a fine-tuning. It is a consequence of the mathematical structure of supersymmetry, which relates the couplings of the partners in a precise way. For supersymmetry to solve the hierarchy problem without introducing a new fine-tuning, the superpartners should have masses not too far above the electroweak scale, roughly below 1 to 2 TeV. This is the famous naturalness argument that predicted new physics at LHC energies. The stop quarks, the supersymmetric partners of the top quark that give the dominant contribution to the Higgs mass correction, should be below approximately 1 TeV for the most natural versions of supersymmetry. The LHC has searched extensively for stop quarks and found none. The current lower limits on stop masses from direct LHC searches are approximately 1.1 to 1.2 TeV for the most model-independent search strategies. This pushes the allowed stop masses into a regime where the cancellation of the Higgs mass corrections is no longer automatic, but requires some fine-tuning at the level of a few percent. The elegant solution to the hierarchy problem has become less elegant as the mass limits have been pushed higher, though it has not been eliminated. Alternative solutions to the hierarchy problem include extra dimensions, composite Higgs models, and twin Higgs models. Each of these makes specific predictions that the LHC has tested. In the Randall-Sundrum model, extra dimensions produce Kaluza-Klein graviton resonances at TeV masses. In composite Higgs models, a vector resonance analogous to the rho meson of QCD appears at TeV masses. None of these has been found, pushing the mass limits for these models to several TeV in most channels. What the LHC has accomplished by finding the Higgs and finding nothing else is to rule out the simplest and most natural solutions to the hierarchy problem. This is scientifically important. It tells us that if new physics exists to explain the Higgs mass, it is either more complex than the simplest supersymmetric and composite models, or it exists at masses above the current LHC reach, or the hierarchy problem is addressed by a mechanism we have not yet thought of, such as the multiverse anthropic argument. The standard model is incomplete, but the LHC's null results have told us that the incompleteness is not of the simple form we expected. Now let me take you to the specific possibility that I find most scientifically interesting and most underappreciated in popular accounts of the LHC results. The possibility that the standard model itself is unstable. The discovery of the Higgs boson at 125 GeV, combined with the measured mass of the top quark at approximately 173 GeV, has a specific and extraordinary implication for the long-term stability of the universe. The Higgs boson and the top quark together determine the shape of the Higgs potential, the function that describes the energy of the Higgs field as a function of its value. In the standard model, the Higgs field has a specific potential with two features: a local maximum at zero field value and a minimum at a non-zero value, the electroweak vacuum, where the universe currently sits. Electroweak symmetry is broken because the Higgs field has taken a non-zero value in the ground state. But the shape of the Higgs potential at very high field values depends on quantum corrections that involve the top quark. With the measured values of the Higgs mass and the top quark mass, the Higgs potential develops a second minimum at field values far above the electroweak vacuum at approximately 10 to the 12 GeV. This second minimum has lower energy than the electroweak vacuum we currently inhabit. If this second minimum exists, the electroweak vacuum is metastable. It is a local minimum, but not the global minimum. The universe is in a false vacuum, the electroweak vacuum, when the true vacuum is the deeper minimum at high field values. The electroweak false vacuum can decay through quantum tunneling. A bubble of true vacuum can nucleate spontaneously, and the bubble wall, where the field transitions from false to true vacuum, would expand at the speed of light. Inside the bubble, the laws of physics are different. The masses of particles, the strengths of forces, everything determined by the Higgs field value would change. The good news is that the tunneling rate for vacuum decay in the Standard Model, calculated from the Higgs and top quark masses, is extraordinarily slow. The expected lifetime of the electroweak vacuum is approximately 10 to the 139 years, a number so vast that it makes the age of the universe seem instantaneous. The false vacuum will not decay for incomprehensibly longer than the current age of the universe. The bad news is that if new physics exists beyond the Standard Model that modifies the Higgs potential at high field values, the stability analysis changes. Some extensions of the Standard Model make the vacuum more stable. Others make it less stable, potentially even absolutely unstable, if the new physics creates a lower minimum at lower field values than the one already predicted by the Standard Model. If the LHC's high energy collisions are somehow probing the Higgs potential at field values near a new minimum, the implications would be dramatic. I want to be clear that there is no current evidence that the LHC has destabilized the vacuum or is approaching a dangerous regime. The energy scales at the LHC, up to a few TeV in center of mass energy, are far below the field values where the Higgs potential turns over, which are at 10 to the 10 GeV or above. No vacuum decay event has been observed or is expected from LHC operations. The suggestion in the video title that CERN may have opened the door to a new reality is a statement about the precision measurements pointing toward new physics, not a suggestion of actual danger. But the metastability of the electroweak vacuum is a genuine, calculated result of the Standard Model, and it means that our universe exists in a specific and physically significant sense on the edge of a phase transition. The laws of physics as we know them are not the ground state, they are a long-lived metastable state. And the discovery of the Higgs boson at 125 GeV is what told us this. Let me now return to the question that the LHC anomalies raise in a broader sense. If new physics exists at energy scales above the current LHC reach, what form would it take and what evidence might we have for it? The most powerful indirect evidence for new physics at high energy scales comes from measurements that are sensitive to the contributions of heavy particles in quantum loops. Even if new particles are too heavy to be produced directly, they contribute to observables through virtual processes. The precision measurements of Higgs couplings, the muon anomalous magnetic moment, the W boson mass, and rare B meson decays are all sensitive to such contributions. The specific particles that most commonly appear in beyond Standard Model theories and that could explain multiple anomalies simultaneously are leptoquarks, Z' bosons, and additional Higgs bosons. Leptoquarks are hypothetical particles that carry both quark and lepton quantum numbers. They are predicted by several grand unified theories which attempt to unify the strong, weak, and electromagnetic forces at very high energy. Leptoquarks naturally couple to both quarks and leptons, which means they can contribute to processes involving transitions between quarks and leptons, including B meson, decays into leptons, and radiative corrections to the muon anomalous magnetic moment. Models with specific types of leptoquarks have been constructed that explain the B anomalies and the muon G two deviations simultaneously, with leptoquark masses in the range of 1 to 5 TeV, accessible in principle to LHC searches. Z-prime bosons are heavy neutral gauge bosons beyond the standard model Z boson. They arise in many extensions of the standard model's gauge symmetry, including models where the B-L symmetry, baryon number minus lepton number, is gauged. AZ-prime boson coupling specifically to the second generation of quarks and leptons could explain the B anomaly pattern, where the deviations cluster in processes involving muons and strange or bottom quarks. Direct searches for Z-prime bosons at the LHC have set lower limits on their mass of several TeV in many models, and searches continue. Additional Higgs bosons arise in 2 Higgs doublet models and in supersymmetric theories. If the Higgs sector contains more than one doublet of scalar fields, the physical spectrum includes multiple Higgs bosons with different masses and couplings. The heavier Higgs bosons would be produced at the LHC if their masses are below the kinematic threshold, and they would affect the precision measurements of the lightest Higgs bosons couplings through mixing. The current precision Higgs coupling measurements constrain the mixing between the observed 125 GeV Higgs and any heavier Higgs boson. The constraints are at the 10 to 20% level, which still allows for new Higgs bosons with modest mixing at masses above a few hundred GeV. Let me connect this to the larger question that the title raises. Has CERN opened the door to a new reality? By which I mean, have the LHC's measurements, both the direct discoveries and the precision anomalies, given us evidence that our current understanding of physics is incomplete in a specific and testable way? I think the honest answer is yes, with significant caveats. The standard model is incomplete in ways that are known and acknowledged. It does not include gravity. It does not explain dark matter. It has unexplained parameters. These are acknowledged incompleteness. But the LHC has also provided something more specific, a set of precision measurements that collectively point toward new physics at energy scales accessible to near-future experiments. The muon anomalous magnetic moment at 4 sigma, the Higgs to Z gamma excess at 3.4 sigma, the persistent W boson mass tension, and the remaining B anomalies are individually uncertain but consistently point in the direction of new contributions to standard model processes. They are not yet evidence of a new particle or force, but they are hints that the standard model's accounting of quantum loops is incomplete. The door to a new reality is this. If any of these anomalies is confirmed by future measurements, if the muon G2 discrepancy survives the resolution of the hadronic vacuum polarization controversy, if the Higgs to Z gamma rate is confirmed at 1.9 times the standard model prediction, if the B anomalies persist with more data, then the standard model has a specific crack at a specific location, and the new physics that explains it must exist at a specific energy scale accessible to the next generation of experiments. The 100 TeV future circular collider proposed at CERN and the competing proposals for a muon collider or an electron-positron circular collider would probe energy scales and precision levels that would either confirm the new physics or push the mass limits for any explanation of the anomalies to beyond the reach of any foreseeable accelerator. Now let me take you to the specific possibility that I find most scientifically interesting and most underappreciated: the metastability of the electroweak vacuum. The discovery of the Higgs boson at 125.09 GeV combined with the top quark mass at approximately 173 GeV has a calculated and specific implication. The Higgs quartic coupling lambda, the parameter that determines the shape of the Higgs potential at high field values, runs with the energy scale according to the renormalization group equations. The top quark-Yukawa coupling, large because the top is heavy, drives lambda negative at high energy scales. When lambda turns negative, the Higgs potential develops a second minimum at approximately 10 to the 10 to the 12 GeV, deeper than the electroweak vacuum at 246 GeV. The universe currently sits in the electroweak vacuum. This is a local minimum, but not the global minimum of the Higgs potential. The tunneling rate from the false electroweak vacuum to the deeper true minimum is calculated using the Coleman-de Lucia bounce technique. The result is a vacuum lifetime of approximately 10 to the 139 years, some 10 to the 129 times the current age of the universe. No danger in any practical sense, but a profound statement about the nature of our universe. We live in a false vacuum. The laws of physics as we experience them, with the particle masses and force strengths we observe, are not the ground state. They are a long-lived metastable accident, a local minimum in the space of possible universes. The true vacuum with different Higgs field value has different physics, different particle masses, different force strengths, possibly different effective space-time structure. We cannot calculate what the true vacuum is like without knowing the full high-energy physics above the LHC's reach. A bubble of true vacuum can nucleate anywhere in the universe at any time through quantum tunneling. The bubble wall expands at the speed of light, converting the false vacuum to the true vacuum as it passes. Everything inside the bubble experiences the true vacuum physics. The bubble has not formed in 13.8 billion years of cosmic history, consistent with the calculated lifetime, but the physical possibility is real, calculated from the measured standard model parameters. This is what the Higgs boson at 125 GeV tells us about the universe. Not just that the standard model is complete, but that the standard model, with its measured parameters, predicts that we live in a universe that is not in its ground state. The new reality that CERN has opened the door to is already here in the equations. The new reality that CERN may be opening the door to is not a different universe or a different set of physical laws. It is a deeper layer of the same physical laws, the layer below the standard model, where the particles we have been missing might finally come into view. The new reality that CERN may be opening the door to is not a different universe or a different set of physical laws. It is a deeper layer of the same physical laws, the layer below the standard model, where the particles we have been missing might finally come into view. Let me describe what the next generation of experiments is designed to find. Because the program of precision physics and direct searches continues beyond what the current LHC can do. The high luminosity LHC, the HL-LHC, is an upgrade of the current machine that will begin operations approximately in 2029. It will run at the same collision energy, 13 to 14 TeV, but with approximately 10 times the instantaneous luminosity, meaning 10 times more collisions per second. The total data set accumulated over the HL-LHC era will be 10 times the total data set from all previous LHC runs combined. The HL-LHC will measure Higgs boson couplings with precisions of approximately 2 to 5% compared to the current 10 to 20%. If the Higgs to Z gamma excess at 1.9 times the standard model value is real, the HL-LHC will confirm it at well above 5 sigma or rule it out completely. The muon anomalous magnetic moment measurement will be further refined by the Fermilab muon G2 experiment's final results, and the theoretical hadronic vacuum polarization controversy will be resolved by new measurements from CMD3, Baybar, and lattice QCD. The W boson mass will be measured more precisely by ATLAS, CMS, and LHCb. The HL-LHC direct search program will push the mass limits for supersymmetric particles, leptoquarks, Z-prime bosons, and other new physics to approximately 3 to 5 TeV for strongly produced particles and somewhat lower for electroweak production. If any of the precision anomalies is explained by a particle at these masses, the HL-LHC has a good chance of discovering it directly. Beyond the HL-LHC, several next-generation collider proposals are under consideration. The Future Circular Collider at CERN, the FCC, is a proposal for a 100-kilometer circumference ring that could first operate as an electron-positron collider, the FCCE, at up to 365 GeV, and later as a proton-proton collider, the FCC-HH8 at 100 TeV, center of mass energy. The FCCE would measure electroweak parameters and Higgs couplings with precisions far beyond the LHC, constraining new physics at mass scales up to approximately 10 to 100 TeV indirectly. The FCC-HH would directly probe mass scales up to approximately 50 TeV in direct production searches. The International Linear Collider, proposed for construction in Japan, and the Compact Linear Collider at CERN would provide electron-positron collisions at hundreds of GeV to several TeV with precision measurements of Higgs properties at a level that could detect deviations from the standard model at the percent level. A muon collider, currently the subject of intense theoretical and technical development, would accelerate muons to energies of several TeV in a compact ring. Muons are 207 times heavier than electrons and thus produce much less synchrotron radiation, allowing them to be accelerated in a circular machine at much higher energies than electrons. A muon collider at 10 TeV center of mass energy would be the most powerful precision machine ever built, with simultaneous reach in both direct production and precision measurements far beyond any other proposed collider. Each of these proposals would provide qualitatively different information about what lies beyond the standard model. The precision measurements would constrain the energy scale of new physics through indirect effects. The direct searches would probe specific particles if they exist within the kinematic reach. The crucial point is that the current anomalies, the muon G2, the Higgs to Z gamma, the W boson mass tension, all point to new physics at energy scales between 1 and 10 TeV, accessible to the HL-LHC, and definitively covered by the FCC or a muon collider. If the anomalies are real, the next generation of experiments will find the new physics directly. If the anomalies dissolve as more data accumulates and theoretical uncertainties are reduced, and if the direct searches at HL-LHC and future colliders find nothing, we will face a deeper crisis in particle physics than the current one. The hierarchy problem will remain unsolved. The standard model will remain the final theory at accessible energy scales with no explanation of its fine-tuning. The vacuum will remain metastable without any new physics to explain or prevent its instability. That outcome is also interesting, though in a less comfortable way. It would force a fundamental reconsideration of our theoretical framework, potentially including the naturalness arguments that have driven the field for 40 years. What physics can say is that the current anomalies are real measurements. The standard model predictions they deviate from are real calculations, and the gap between them is either the first glimpse of a new layer of reality or a set of systematic effects that will dissolve with more data. We are in the most interesting period of particle physics since the Higgs discovery, and the experiments of the next decade will tell us which it is. If the anomalies and the vacuum stability picture look different after understanding the full context, tell me in the comments. Tell me whether you find the precision anomaly approach to new physics more or less convincing than the direct production approach that the LHC was originally designed for. Tell me whether the metastability of the electroweak vacuum changes how you think about the long-term future of the universe. And subscribe if you want to stay at the frontier where the most precise measurements in physics are probing the edges of everything we know.